So in this video, we're going to show you how to do what is commonly referred to as a two-sample t-test using Microsoft Excel. We're going to go a little bit further than just using Microsoft Excel. We're going to leverage called the data analysis toolkit. It's right here. It's under your data tab. You do have to sometimes add that. So if you need to add it to your full version of Microsoft Excel, go ahead and Google how to add that there. But we're going to be leveraging this piece of technology to do this two-sample t-test, and I'm going to show you why. So previously, we've talked about different hypothesis tests. We did the one-sample hypothesis test previously. And in order to calculate any of these hypothesis tests, we need a test statistic. And this is our test statistic for the two-sample t-test. Now, this is a little more complicated than it usually is. Usually this calculates to 0, so I don't have to worry about it. But what really makes this a huge pain in the butt, where we're not going to create a template, and even though you guys know I'm a huge fan of those templates, is right here. This is the degrees of freedom that we would need in order to find the p-value using this test statistic. This is very, very ugly. It is very easy for us to make some sort of numerical error. You can estimate this degrees of freedom using the number in the first data sample plus the number in the second data sample and subtracting by 2. This is an estimation of degrees of freedom, but it is not very good. And we have technology nowadays, we could do a lot better than that. So let's go back to our calculator for a second. So here in this calculator, I have two different data sets. It doesn't really matter what those data sets are. I have data set 1 and data set 2. One of the beautiful things about two-sample hypothesis tests is I don't really care if the two data sets are of the same size, and they're not. If we take a look at these, I click here, and I say, okay, there's 34 in this data set, and there is 48 in this data set. It doesn't matter because we're making hypothesis around the true mean of these two different data sets population. We do want to make sure that these are independent observations. They're from two different populations, and they are at least 30 observations. Now, if we know that the parent distribution is normally distributed, don't have to worry about that last little bit. But for this, we're okay because we have more than 30 observations. Now, like I said, we're going to leverage the data analysis toolkit. So I click on the data analysis toolkit, and it brings up a whole bunch of different options. We're going to do the two-sample assuming unequal variances. I will put this out for you once and once only. Never, ever, ever use assuming equal variances. This is a throwback to when we didn't have technology that we could leverage. So don't use that. We will be using the paired in a future video, and we'll never use the z-test. That's also a throwback from hinter years when we didn't have the ability to do all this with a computer. So I'm going to say okay here. It tells me everything that it's needing. You see, I did this problem previously. It's saying, hey, what's variable 1 range? Well, nice enough. It doesn't work with all of the different functions, but this one it does. I can just click on A. Boom. Hey, it's using all the A. That's nice because if I expand my data set, I know I'm just taking column A. Column B here, my hypothesized mean for this problem is 0. For most of the problems that we're going to be doing, the hypothesized mean, most to all of the problems we're going to be doing, the hypothesized mean is always going to be 0. I do have labels in this data set, so I do click on labels. And my alpha equals 0.05 is not super important because it is going to give me a p-value so I can make my determinations on whether to reject or fail to reject the null hypothesis based on my p-value as opposed to some arbitrary alpha. I like to output it to a new sheet so I don't change that. So the only things I really changed in here were the variable 1, variable 2, and sometimes this won't be clicked. So I had to click on that. Okay, I say okay, and I go over to my data. Now, what is this telling us? What this is doing is it performs a two-sample t-test assuming that this So my alternative hypothesis is always for the one-tailed test going to be H alternative is going to be mu smaller is less than mu bigger. Yeah, my alternative. It does give you the p-value for a two-tailed, and it gives you the p-value for one-tailed. What am I talking about with smaller versus bigger? It is assuming that you meant for this mu to be smaller than this mu, for data set 1's mu to be smaller than data set 2's mu. It just so happens that is what we were interested in here, or we were interested in two-tailed. It's up to you. The p-value here is pretty small. With this output, what am I really concerned with? Really, more than anything, I am concerned with these two values. If my problem calls for a one-tailed hypothesis test, I'm going to look at this. That is my p-value for my one-tailed hypothesis test. If it's two-tailed, I go right there to my two-tailed. You'll notice that this number is twice that number. What's nice here, though, is I got my test statistic, I got my degrees of freedom with that ugly, ugly formula. It does calculate it using the ugly formula. A lot of other software will calculate it with the shortcut. You like having the full ugly value, all right? So download the data analysis toolkit. It will help you with these two-sample assuming unequal variance t-tests.